Welcome back to ECE 442-542. Here we're going to work one more example, and this one is with respect to the arrival angle. How do we arrive, or what direction do we arrive at the complex zeros at? And here we have 3 poles and 2 complex conjugate zeros. This is rule number 5 as we have labeled them for this particular semester, and we want to know how do the angles now approach, or how do the branches of the root locus approach these zeros. In this particular case, let's just look at what we have. We have a pole at the origin, we have another pole at 1/2, and we have another pole at 1. And then these zeros are actually in the left half plane at 1/2 plus and minus j1/2. And for this particular collection of poles and zeros, we can now start looking at which pieces of the real line belong to the root locus. We know that these two are going to come together and meet. Maybe what we don't know is how they approach those zeros. Do we go like this and then have this pole go that way? Or, to look at another illustration, we aren't changing the poles and zeros locations, and the way that they behave will actually depend on the relative spacing of these poles and zeros. But it could be, because of the way that these are spaced, that these two, we still have the same segments, but now these two might actually go up and over and re-enter. And then, in fact, this one comes towards the left as this one now approaches, and now maybe these two go towards the zeros. And now which root locus pattern do we have? And in fact, you can look at the answer in the back of the book and use MATLAB and figure out which pattern very quickly by putting this transfer function into MATLAB, issuing the rlocus command, and see which of these particular patterns for the root locus you might have for this particular pattern of poles and zeros. There's a couple of guides that we can actually use to determine what pattern we might have. In this case, on the left, our angle of arrival is less than 90 degrees. In this one, our angle of arrival is closer to 180 degrees. So based on if we calculated the angle of arrival, we might be able to determine which of these particular patterns might be in play. Another way to second check that is to look at how K behaves as we move along this left half or real axis portion of the root locus. Does K as a magnitude just keep going up? Or in this case, it actually needs to experience, what do we know happens at a re-entry point? This is now going to be a relative min for K, and here is a breakaway, so this would now be a relative max. So if we plotted K, K would be very big here, but then it would be decreasing at that point, and then it might be increasing there, but we know that it goes to 0 at the origin. So here, if we plotted K with respect to z values from, let's say, -3 to 0, we would see a K curve, a magnitude curve of K, experiencing a relative min and then a relative max. and not monotonically increasing as we moved from 0 to minus infinity, as we see on the left. So now we have a couple of different ways that we could check which of these patterns might actually be valid. And let's go ahead and look at what we could do for the arrival angle. Let's just resketch our picture. We have our zeros here. We have poles, 3 different poles. We have a pole zero excess of 1, so we know we really only have the one asymptote going off to minus 180. And now we can start calculating these angles. Let's say that we call this angle theta sub z sub 2. Then we want to know very close to this 0. Here's our epsilon distance away. Let's say this is our angle of arrival, alpha sub a, and then we have all of the angles from these 3 different pole locations. Suppose we call this, since this is at a value of 1, let's call this theta sub p1. This was at 1/2, so there's a 2 associated with it. Let's call that theta sub p sub 2. And here, this was at the origin, so let's call that angle theta sub p sub 0. Which means that using the phase angle condition, we should be able to compute this alpha sub a, the angle of arrival. We have the sum of the zeros angles minus the sum of the pole angles. And if that epsilon point right here, it belongs to the root locus, then this phase angle condition, or these algebraic sums of these angles, has to be equal to minus 180. We can plug in some of these immediately. Theta sub z sub 2, we're looking straight up, so that one is 90 degrees. Alpha sub a is unknown, but now let's see, theta sub p sub 0, can we compute that? That's just an opposite side of 1/2. That was at 1/2, and we're over 1/2, so the adjacent side is 1/2. Theta sub p sub 0 is 135 degrees. Theta p sub 1, that was the angle over here due to the pole at 1. And now maybe it's easier to deal with these acute angles. So theta sub p sub 1, the way I like to look at that, is 180 degrees minus this acute angle. And the acute angle had an opposite side of 1/2 and an adjacent side of 1/2 plus 1, or 3/2. So now we have 180 minus the inverse tangent of a third. If we looked at the inverse tangent of 1/3, that ends up being 18.43 degrees. If we add all of that up, 180 degrees minus 19 degrees, we should be close to 160. And in fact, we have 161.56 degrees for theta sub p sub 1. Theta sub p sub 2 was the angle associated with the pole at 1/2. And again, looking at the acute angle, we know its vertical distance, or opposite side, is 1/2. We now have 180 degrees minus the inverse tangent with an opposite side of 1/2 and a adjacent side of 1/2 plus 1/2, or 1. This angle now, inverse tangent of 1/2, hopefully I'm plugging these into the calculator correctly, is 26.5, or 26.6, so that we subtract that from 180 and we get 153.4 degrees, which is a little bit less of an angle than what we moved through at the pole at 1, and that seems to make sense. Now if we add all of those up, we had theta sub A, or alpha sub A, plus 90 degrees minus 135 degrees plus 161.56 degrees plus 153.4 degrees equaling minus 180 degrees. If we add all of those up algebraically, hopefully we end up with an arrival angle of minus 180 plus minus 90 degrees. So now I'm simply pushing everything over to the right-hand side, and we now add all of those pole angles. Doing that, we actually end up with 180 degrees. So now our angle of arrival is coming in at 180 degrees to those complex zeros. And that seems to indicate that in fact we might be dealing with a root locus pattern that looks more like what we see on the right. And in fact, we can look at that in MATLAB. So let's just go ahead and do that. Let's check the answer in the back of the book by looking at what MATLAB would provide to us. Here is our transfer function, the numerator polynomial. Here's our denominator polynomial written as a vector. Our sample period is unspecified, and that's what MATLAB is telling us. And here is our transfer function. We could have looked at the zeros and the poles of that to verify that, but I'm going to go ahead and just compute the root locus. That's in my first figure here. So if I scroll down to the first figure, and voila, there is our root locus. Now look and examine this. Our axes are not really square, meaning this distance is not the same as our vertical distance, and so these angles and shapes will be a little bit distorted unless in MATLAB you say axis square and square it up, and then your angles will be valid. But you now can see that we are arriving at the zeros since that unit circle. You can see that unit circle is a little distorted. It doesn't look quite like a circle. But these angles of arrival now are 180 degrees coming into those complex zeros. And you can see that I've actually computed some root locus find commands to try to determine what's the gain to get me to that location, what's the gain to get me to z equal to minus 1, and maybe here is our desired closed loop pole locations, the gain to get me there. And maybe I've called that k sub delta. I don't know what I've called this. Maybe k sub plus, and this might be k of minus 1. And you can now try to determine what those are with the G locus, or with the R locus find command. Here you can see that I've now located my crosshairs at 0.68 plus 0.J73, and that's at a gain of 0.29. What did I call that? Did I call that now my K plus? Then I went ahead and found what is the K at minus 1 to make sure that I actually exited the unit circle. I'm sorry, entered the unit circle at a gain of 0.29, exited the unit circle at a gain of 0.29, and this particular pole at the origin hadn't yet escaped out the unit circle at z equal to minus 1, because that gain is 5.9. The gain here, what was this gain? About 0.29. And if I wanted now to maybe find what this gain was, that's now at 0.74 plus j point. So now I'm calling this, I think, my K triangle. I use that gain to determine a closed loop transfer function with the feedback command. I find the closed loop poles. They're all inside the unit circle. And my second figure, I actually compute or look at the step response. And that's right here with the characteristics with the right mouse click. I now have a 12% overshoot, a settling time of a little bit more than 14 samples. And this last set of commands, it looks maybe a little cryptic, but now I'm examining the angle, the magnitude of K. Here I'm calling it F, and my Z is now T. So I don't know why I used all of these different variables, but here is a for loop from t ranging from -2 up to 0, and I'm sketching k, the magnitude of the gain along that. And now you can see that around 1.8, minus 1.8, is a relative minimum, and a relative maximum is around there. And that should be consistent with where here's a relative max and here is a relative min for the value of k in that particular root locus. And that's what this is illustrating. Here is our relative max for a breakaway point. Here is a relative min of k. This is now the magnitude of k for values of z between -2 and 0. And maybe I should have extended this z to -3 so that you could see this curve going up, and maybe it would be more clear that that is a relative minimum somewhere about around -1.8, which is what that's showing. And then we have a relative max a little bit to the left of -1, and that's what is shown here. That's now a way to think about these angle of arrivals for complex zeros and how you might use those to your advantage in analyzing or designing controllers.